So we had a few questions on this problem here, so I thought it would be good to go over it. So we'll go ahead and draw our coordinate axis here. And so you're given one particle, and its x distance is given as 15 centimeters. So I'll write that as 0.15 meters and 5 centimeters. So this is not perfect, but something like this. And so here's the first particle, Q1, and it has a charge of 9.5 microcoulombs. Our second particle is at a position over here, given as 4.4 centimeters, so 0.44 meters, and then over here 11 centimeters. So first of all, they weren't very kind to us when they were doling out the positions of these. Okay, so it's kind of complicated. But the first thing is you want to make sure that the picture I've drawn makes sense. So this is the correct picture, I think, for drawing this. And so now what I'm going to be very interested in is sort of this distance here and this distance right here. And so, 0.15 minus 0.044, when I did that, I got a distance of 0.106 meters for that one there. So that's the distance between the two particles in the x direction, if you will. And the distance between the two particles in the y direction is 0.06 meters. And the reason I'm interested in these is because what I really want is this distance here, this hypotenuse, right, which I'm going to call r. And so r is the distance between the two particles. That's how that's defined. And so for us here, it's just 0.016 squared. So I'll go like this. The square root of 0.06 meters squared plus the other one, 0.106 meters squared. And so I find that r, the hypotenuse, and when I did it, I got something like 0.121 meters. So, so the first thing I like to do is then just calculate, what are we trying to find here? We're trying to find the force on this particle here, on the negative particle. So I like to find the magnitude. So it's K Q1 Q2 over r squared. And so K is our constant, 9 times 10 to the 9th. I'll just leave out the units because they're kind of nasty. So for Q1 and Q2 it doesn't really matter, but again what I do is I disregard the sign because it's the absolute value we're looking for. So 3.2 microcoulombs, 9.5 microcoulombs, and then of course it's all divided by 0.121 meters squared. So make sure you do this with me, and when I did this I got 18.44 newtons. So now what we want to do is we want to go through and find, because the book gives this to us in x and y coordinates, we want to go through and figure that out from this magnitude. Okay, so this gives us, again, the magnitude of our force. Now, real quick, I saw some people who were using the distances of like the 0.106 and the 0.06. You can't use like the x or y coordinate. You've got to use the actual r, the actual distance between the two particles. Okay, so that's really important. And so here I just cleaned it up. Here's again our force. The next step, once we find the magnitude of the force, is to find the direction. And so we're actually, the problem wanted us to find the magnitude or the force on the negative charge. And so if you look here, the negative charge's direction should go something kind of like this. It should point a little bit that way and a little bit there. And so let's just go ahead, and it's always good to name our coordinate system. So I'll call the traditional coordinate system the x and y coordinate system that we usually do. And so basically what we need to do now is find an angle. All right, and this angle is not the most pleasant angle, so I'll just do my usual trick, which is tangent of my angle is always opposite over adjacent. So why don't you, stop and try to find this yourself right now, and then I'll share what I got here in a second. Okay, so this is my angle. The opposite is 0.16 meters, then kind of like that, and this one here is 0.06 meters. If I grab my calculator, when I did that, I got somewhere in the neighborhood of 60 degrees, 60.5, I think. So 60.5 degrees. And so then if I sort of blow this up here, this is my triangle, okay, I'm going to have a little triangle like this. I'm going to have my x and y coordinates, and so again the hypotenuse here is 18.44 newtons. This is my angle theta, that angle of 60.5, and I want to find, my force in the y direction and my force in the x direction. So my force in the x direction would be here, or at least the magnitude of it. My force in the x direction would be what? 18.44 newtons. And now this is the side that's opposite the angle. So I'd want to say sine of 60.5. Now when I punched that into my calculator, I got 16 newtons when I round up. For the magnitude of Fy, that's this guy over here. That's the adjacent side to the angle. So it would be 18.44 newtons times cosine of 60.5. And when I did that one, I got 9 newtons. And so basically we're all done now. It's just a matter of sort of putting it into, like I like to draw into a form like this. So I say my F net, my vector, is equal to this here. And in this parentheses, here I put the x, here I put the y. So my x is 16 newtons. And now according to my system, my x and y coordinate system, this is in the positive direction, so I get a positive 16 newtons. This one over here, if you look at my vector, it's pointing downward. It's pointing in the negative y, so I'd call this negative 9 newtons. So again, the book does this, and I think actually the book keeps an extra it's like 9.1 or something, but it's just sort of rounding. But the book does this in the I and J way of doing it, which again is fine, but I just end up coming out with an x and a y, and then just when you define your coordinate system, the x and the y is either positive or negative, and I use sort of the traditional x and y. So follow up with any questions you might have. Thanks.